Is that on the video? Did you put?
No.
Okay.
Hi
Miss
guys,
Young,
welcome to 5-2, the normal distribution revisited. Same earrings, same shirt, 5 minutes later from 5.1.
she says we're not changing clothes, and then starts recording. I'm like, wait, what? So you might as well. I guess I just ruined it, but you
It's
know,
okay.
it's okay.
They don't
Nobody
mind.
watches these videos anyway.
Excuse me, a ton of the kids watch my videos, and your videos don't discount us.
Okay.
Okay, so we're back to the normal distribution, and the reason we're talking about the normal distribution again is because from here on out, this is the bread and butter of our course, right? We can't do anything else moving forward if we don't really understand this concept of normal distribution.
And we've done this before, so this lesson hopefully will feel familiar, but we're going to be using this in our sampling, so it's really important. Okay.
So our learning objectives here, calculating the probability that a particular value lies within a given interval of the normal distribution, determine the interval associated with a given area, and determine the appropriateness of using the normal distribution to approximate probabilities. Okay, so we're going to jump right into our first round of essential knowledge. Unlike the last video that had one piece of essential knowledge, this one has like 11. But it's all review, so.
Yeah, we've done all of this before, okay, about the normal distribution. So, yeah, the continuous random variable will take on any value, and it's be distributed from a mean and a standard deviation. So we're going to use all that. It's going to be that bell-shaped curve with the peak at the mean. And then we're also going to remind ourselves about the probability and what the area under the curve means. We'll talk all about that when we get into the actual graphs.
Yeah. So first question for you. Data will be collected on the following variables. Which variable is most likely to be approximated by a normal model? Remember, the normal model has that symmetric bell-shaped curve, okay? So this first one says the distribution of the number of books read last week by middle school students, where the right tail of the distribution is longer than the left. The distribution of the number of books read last week by middle school students,
Nope.
Where the right tail of the distribution is longer. So why, Mr. Bobby?
Because of the tail.
Yeah.
If it's not balanced or it's not symmetric, I'm out.
Okay. Second one says the distribution of lifespan in minutes for batteries of a certain size, where most lifespans cluster around the center of the distribution, but with some very low and some very high lifespans.
I'm cool with that.
Maybe this one?
Yeah, I'm kind of cool with that one. I don't know why my nose is off center, but you know, that's okay.
We like the cluster in the center, like some on either side.
Some low and some high. It doesn't tell me how they're balanced, but I'm more happy with that one than the first one.
This looks like a beauty mark on the smiley face and not a nose.
Yeah, and it's probably a birth. Yeah, it's, you know, I'd say Cindy Crawford, but they don't know who she is.
Oh, look her up. She's beautiful. Okay. The distribution of ages in years of the students at a certain college, where most students are between 18 and 22, but ages greater than 22 will probably be more spread out than ages less than 18. So can you draw us a graph? What do we think this is going to look like? Clustered around 18 to 22, that's where most of the students' ages will be.
Yeah, so
now think about this, because this is certain college students. So some students might start early, like around 16. Some might just be like have a late birthday, and so they might be starting at 17. Most students will be 18 to 22. But then you also have people that go back to college later on in life. My mom actually got a second degree out of boredom in her 50s. So like she's gonna be
nobody. Yeah, somebody might be going to college in their 50s, but nobody's going to college at like 3.
Right. So what's that look like, Mr. Bobby?
It would look like that. There'll be a lot of more people's out to the side. Not many, but there'll be people out there that are 40s and 50s that might go back. But there might be the Sheldon Coopers who go at 8 or something.
Yeah, there are
not a lot of them. Yeah,
but probably far more in their 50s than 8.
Right. And even, I mean, but we can't go much younger than even, I mean, I don't know what the youngest person who ever went to college was, but I'm guessing, there's only 18 years below 18 and 50 is 32 years above. So that's
So
spread
that
over
doesn't
here.
feel balanced on either
It's
side
not
of it.
balanced. Yeah. Even if we were going to send an infant to college, that's only a gap of 18 years versus sending somebody who's in their 50s is a gap of 30 something years.
Yeah. So we don't like this one because this feels like
Feels unbalanced.
yes,
Just like
right.
it's kind of like the book one.
Yeah. Skewed right, skewed to the larger numbers. You just
I marked the
off.
wrong one. My bad. Sorry. I'm sorry. I marked the wrong one.
It's okay. We forgive you. All right. The distribution of the number of birthdays per month for the employees at a certain company, where the number of birthdays in each month is approximately equal.
So that means like the graph would look like this. I guess I gave my pen back here. Every month is the same, so there's no bell. Like the graph would look like this. Here's the months, and it would just look like a straight line pretty much. It would look like that.
Yep. Yeah.
Okay, so there's no bump, no bell curve in this one.
Yeah. So we dislike this one as well.
I dislike this one very much so. So I was actually right earlier on. I should have just left my X there.
Last one, the distribution of the length of stay in days in a hospital after surgery, where many patients have short hospital stays, but some stays are quite lengthy and considered high outliers.
So it would look like this, way out there. Again, it's skewed right. There'll be very few people that have short stays, or some of them may not have any. They do this outpatient surgeries a lot of times. So anyway, but there are some people who have complications and have to stay very long. So this one is, again, skewed to the right. So I'm not liking any of these. The only one we like is the Cindy Crawford one.
Yeah. So talking about normal distribution, you really want to think about, will they be clustered around a center with, sort of like a few on either side of that balance each other out, that nice, pretty bell curve. Okay. All right. So next question. Next question says, and I've put the answer accidentally. Claire recorded 50 numerical observations on a certain variable and then calculated the mean and standard deviation for the observations. I can't type. To help decide whether a normal model is appropriate, she created the following chart. So let's just kind of talk through this chart here, Ms. Robbie. Why will this chart help us determine if a normal model is appropriate?
Well, because we got that distribution of we got the standard deviations from the mean being balanced again. We have to add and subtract the standard deviations. And so somewhere in the middle here should be, I don't know if you meant to put it there, but right there, that's where X bar should be. Somewhere in there. I'm not sure I have it exactly in the center. But so we're going one standard deviation below, one standard deviation above, and same thing. So we're looking for the symmetry of the numbers.
Right. So it says, in Claire's chart, the letters A, B, C, D, and E represent the number of observations falling in each interval. Which of the following list counts for A, B, C, D, and respectively is the best indicator that the variables can be modeled with a normal approximation?
And we're going to come back to this a little later, but we know that there's a certain amount within each of the intervals. Is that okay if I talk about that now?
Yeah,
or
you can talk about whatever. It doesn't matter. This is just
okay.
all reminding us.
Remind you right here, within one standard deviation was 68%. Okay, so we know we're looking for 68% of the data to fall within one standard deviation. So based on C, like this region C should have 68% of the data. Now we have 50 observations, so 68% of 50 would be 34. So I'm liking this one as but I wouldn't discount this one or this one. I can already discount this guy because there are more than 50 total. okay? And I also, let me see here. This one seems a little, well, I mean, it's not terribly off from 34, but I want about 34-ish, okay, in that region there, okay? So,
Just to be clear here, if we had 100 numerical observations, I would expect to see 68 here because that's 68%. But because we only have 50 numerical observations, instead of having 68, I would have 34. And that's where that 34 number is coming from. I'm not sure if you caught that. That's why he's liking that number so much. So this is,
yeah, I'm like, but the others aren't like out of the question, but the best answer is that first one so far.
yeah. And really and truly, like that, because none of the other ones are 34, I'm guessing, okay, this is probably not going to work. And then there's some that's like, okay, there's way too big of a skew here, right? Like 38 for 2, that 4 and that 2, like if you remember the way it works, it's not half. There's quite a large fall in the curve, okay? So yeah, I agree that 1,734.71 is the correct approximation here for that.
It's the best estimate of those. And it's also because outside of 2 standard deviations, remember, but within it's 68 and then 95. So that means I have 5% of my data outside of that. And so 5% of 50 would be about 2.5, which they've got 1 and 1 here, which is close to 2.5%.
Yeah.
But we're going to talk more about that too.
Yeah. So remember when we start going into this, that when we look at the normal model, so that's what you see here is the normal model, that the normal model gives us the proportion of something, the percent of something, or the probability of something. Those are 3 kind of the same things, but we just use different wording for different problems. So if it says, what is the proportion, or what is the percent, or what is the probability, and you know it's a normal distribution, then you know you're looking at the area underneath the curve, right?
Is this like, am I seeing this wrong? Is that P missing?
What P? Probability, percent, proportion. What P?
I'm not seeing, all I'm seeing is row portion. I guess maybe my screen is messed up.
Oh,
Right there,
on my screen it says proportion.
Oh, now it's fixed. Okay. Something was glitchy in Zoom. Sorry.
Oh, okay. So when we're looking at the normal curve here, remember directly in the middle is your mean, okay? And then to the right of the mean is 50% of the data, or 0.5 in the probability, or 0.5 in the proportion. And to the left is 0.5, 50%, however you want to think about it, okay? So we could literally color that in if we wanted to for 50%. Another thing to remember here is we have a calculator that will give us that area underneath the curve using the normal distribution. And we can actually pick lower and upper bounds in the calculator, okay? If we wanted to talk about percentiles, because we did percentile as well, and I don't think I have an example of this, but I think it might be worthy of talking about really quick. Remember, percentile is like if I'm in the 99th percentile, that means what, Mr. Bobby?
That means you are higher than 99% of all the people who came before you.
Okay, so if I wanted to draw a model, that's right, of 99th percentile, my lower bound would be what?
Negative infinity.
Negative infinity, that's right. And my upper bound would be?
Positive infinity. That's the labels on the x-axis.
My upper bound for 99.
Oh, the upper bound would be 0.99. Sorry.
Yeah.
Sorry.
Yeah.
I'm thinking about it just goes on forever and ever.
But, yeah, but we're stopping it at the night. Now, if I were the 74th percentile, my lower bound would be still negative infinity. My upper bound would now be 0.7, because that's going to give me all the probability, all the proportion, all the percent, all the way up to that point, okay? Now, that's only with percentiles for the most part. Most of these types of normal distribution problems will say like at
Well,
least,
yeah.
or greater than, or between. So we're going to look at some of those examples as well. But I just wanted to remind you that the normal curve, these are the three things that it says, this like proportion, percent, and then probability in the problem generally. And somewhere it has to say normal distribution. Okay, so here's that empirical rule that Mr. Bobby was referring to earlier, just so you can reference it again.
You don't
68.
have to know to the second decimal place.
Yeah.
Generally, 68, 95, and 99.7 are sufficient for most applications, most situations.
Yeah, yeah. So this is just a little reminder for you. Pause it, put it in your notes if you've forgotten. All right. Some more essential knowledge. And I'm not going to read all this to you. I think you will remember a lot of it. You might not remember z-scores. So I do want to talk a little bit about z-scores just so you remember what it is. I don't want to reteach an entire 3 lessons, but I think it's worthy of saying this. Mr. Bobby, do you remember talking about why we go to z-scores instead of just using?
It allows us to standardize how the data are spread apart. The data will be a certain standard deviation away. So it allows us to compare apples to oranges in a sense.
That's right. So we did a problem, I think, comparing male height or a boy's height to a girl's height for their averages and saying like who would actually be considered tall. Would the boy be tall or would the girl be tall? Because the boy is actually taller, but when you start looking at what's normal, what's expected for their gender and their age, it turned out the girl was tall within the girl population, but the
all right,
boy.
we get it. Your daughter's short. All right, we get it.
So the point here being that we use z-scores to be able to compare whatever, 2 populations that might not be the same, and how that data falls within those populations. Okay, and to find a z-score, we do value minus mean divided by standard deviation. Value minus mean divided by standard deviation. This is a formula that's not going away, so please make sure that you remember this because it's going to come back and come back and come back. All right, let's look at a problem, and then we'll be done.
All right, I'm getting my friendly neighborhood calculator out.
Okay, I hope all of you at some point have watched this movie.
Oh, don't put us at risk.
Okay, so after accelerating for 20 seconds, the DeLorean sports car, do you think they know DeLorean?
Oh, you're killing me, Smalls.
This is Back to the Future. If you've never seen all the Back to the Future movies, please, over Christmas break, do yourself a favor and go watch them all. All right, after accelerating for 20 seconds, the DeLorean sports car has a wide range of speeds that it can achieve depending on traction. The distribution of speed follows an approximately normal distribution with a mean of 80 miles per hour and a standard deviation of 7.7 miles per hour.
And I'm typing in those numbers into my calculator here for the mean and the standard deviation, and I'm just going to, and I'm finding my normal CDF command.
Okay, so while he's doing that, I'm going to open my annotation tool so that I can draw you a picture here. Okay, so remember my mean of 80 miles per hour, that goes in the middle of my curve. Okay, and I have a standard deviation of 7.7. So I'm going to draw a picture. I'm going to draw a couple of standard deviations just so I can reference this and know kind of what this problem is asking me. So I'm going to go out just a little further. So my first standard deviation is 87.7. Mr. Bobby's trying to go straight to the answer, but we need a good visual here. And then second standard deviation would be 7.7 more. So let me not math that wrong because that would be embarrassing. 87.7 plus 7.7 is 95.4. 95.4. And then remember on the other side of the mean, he's actually subtracting 7.7 to get the standard deviations on the other side. Couple of reminders. Remember, one standard deviation from the mean is actually area to the right and area to the left. So if I say how much is within 1 standard deviation, I'm actually asking for that entire area. Okay, I would have to say 1 standard deviation to the right if I only wanted to talk about to the right. Just a reminder, just a reminder. All right, so now that I have a picture drawn of this situation, I can probably answer some questions about it, okay? So it says, what percentage of the runs will the DeLorean reach a speed greater than 87.8 miles per hour? 87.8 miles per hour.
Now, oftentimes they would use this number, like they could use this number and ask you to do it without a calculator, because we know we have 50% that are less than 80. And then this part between 80 and 87.7 would be 34%, or half of the 68 we saw earlier. So I'm guessing this is going to be 50 plus 34, but maybe a little more than that. So, and I already showed you, I put it in my calculator. I don't know why I'm getting glare now.
So a speed greater than would be everything to the right. Am I right about that? A speed greater
so
than?
I'm going to start, my lower bound to be 87.8. And then in the calculator, you got to put a bunch of 9s in the upper bound, because I don't really want to sit there and type infinity. I could, but it would take a little while.
Now remember, on the AP test, you would want to actually draw the picture as I've just done here. If you're going to use the calculator, you need to put exactly what you see. The lower bound, the word and the number, upper bound, the word and the number, what the mean is, what the standard deviation is, and then give the answer, which he said is that, I can't see what that is, 15%?
Yep, 15.5%. Now, what I was saying about the 50% and the 34, that's actually what's below. So that area that she didn't shade is about 80-something%, 85%. So we would say
my lower bound is that 87.8. Now guys, I'm doing this because I want you to understand that I don't want you to just put a number. If you just put a number on the AP test, you will not get any credit. Zero, zilch. For the right answer, you will get no credit.
Yep. You have to put the lower bound, the upper bound. Do they have to record the mean and standard deviation?
Yeah.
Yep. You got to. So you're gonna do the mean.
This would go faster if you would just write this. And I'm gonna put units here. I'm gonna put units, and then I want to put my answer in context. I think it's important to put your answer in context here so the reader really knows that you understand what your answer is. So, you know, you want to say something like, 15.5%. I don't know what he's writing.
The runs, are greater than 87.8
miles per hour.
Yep. Yeah. I'm getting there. My iPad's being snarky.
And then that's it. Nice and easy.
If you could read my handwriting. Sorry for the iPad today.
Okay. Next question says, what percent of the runs will the DeLorean reach a speed between 64.6 and 87.8?
All right, so the lower bound would be 64.6. The upper bound would be 87.8. And again, I could put units there. X bar would be still the same, 80. And the standard deviation would be 8.7. Oh, sorry, 7.7. And so I need to then go to my friendly neighborhood calculator. And notice I've got that in there. I don't know why I'm getting glare now. There. So I can arrow back up to it and hit enter and just change. I could, go into the menu, or I could just go in and change the upper and lower bounds. Either way, whatever makes you feel pretty. So 64.6, comma, 87.8. And this time, she shaded in a whole lot more. What? Oh, you typed overtime.
Oh, I'm sorry. I didn't see it.
Yeah.
It
okay.
just
I hadn't pressed enter, Sorry,
Oh,
my,
okay.
all right. So now I have, I had a text box going, I just didn't hit enter. My bad. That's actually and so now when I do the thing in my calculator again, I get 82 point. Now let's talk about what number do I have to report. If I have 82.1717, what should they write down on the paper on the test?
You know, there's
Does it
not,
matter?
yeah, as long as you've shown all of the picture and the upper bound, lower bound, standard deviation, mean everything is shown, then it actually doesn't matter. Like, I usually say give a couple decimal places and you will be fine. I see that Mr. Bobby likes the 1 decimal point. That's fine too.
Yeah, the numbers. I'm running out of place.
This is the weird wishy-washy math, remember?
Okay, and you would actually list the numbers there, but I didn't have enough space because I'm typing. Okay.
You can't see what you typed.
Oh, I should hit enter. How about,
Yeah.
okay, and those numbers should be there, but I ran out of space. I got to get off my text box. Sorry. Or you need to give me more rooms. Okay.
My bad.
So,
Right.
all right. Now, what happens with C?
Well, so it says C.A, copy and paste, get me.
Yeah.
What percent of the runs will the DeLorean reach a speed less than 72 miles per hour? Less than 72 miles per hour.
So we would go here, and we want this part down here. Okay. So now we're going to be, if I'm using my calculator, my lower bound is going to be negative 99999, and the upper bound is going to be 72. Okay. In the interest of not trying to cram a bunch in there, I'm going to just show you what it looks like on my calculator. And then, so it would be negative 99999, a bunch of nines, and then 72. So I would want that in my calculator. Okay, notice I'm still doing 80 and 7.7. That's never changing, at least as long as I'm in this problem. And so what do I get as an answer?
Looks like 14.9%.
14.9%. Okay. So do you want to type that up, or are we okay?
I think we're good. I'll throw the answer on there. I need my annotation tool. So we about 14.9%. Is that what we said?
14.9%
of the runs will be less than 72 miles per hour.
I'm very inclined to think this is not going to happen where you're doing the same problem over and over on the AP exam. You're going to do it once. I think we could be okay here because we've already limited it or explained our mean and standard deviation in prior ones. And we have our limits included in the summary that she wrote. But, on an open response, you're probably only going to do this once.
Yeah.
So you're going to have to explain it. Okay. What you are going to have to do that's different is in D, when part D, you're going to actually have to find the boundary. We want to be in the top 15%. So we're actually going to have to go backwards from an area. Okay.
And get rid of all that.
Yeah.
So we want to be in the top 15%. So there's maybe a reason I put C in there, because did you see the visual of what 15% on the bottom end look like? Right? We saw that. So we should have some idea of what 15 on the top end look like, right? Of 72, because this is symmetric, we should be able to say, okay, well, looks like 72 is just below 1 standard deviation on the outside, right? So we should be able to go to a similar place on the right side and kind of have an idea of where that number is going to fall, so that we're not, when we get an answer, we're not just blindly saying, okay, that answer is potentially right.
I know why you did this. I now know why you did this problem.
Okay, so what do we do? How do we solve this problem, Mr. Bobby?
Okay, well, if this greenish area that she made is 15%, then the other is 85%, right? So I want you to note this part over here is 85. Okay. So this is always left-handed. You always need to know, like she wants 15, the other is 85. So I'm going to use a command called inverse normal. And you have to put in the left side area you want, 85%.
Will you show them the screen that's on so that they're
Menu,
not curious?
probability, distribution. It's where you get the normal CDF, you go down to number 3, inverse normal. And when you hit enter, it looks like this. So you're gonna have to enter the area that you want, but it's always the left-sided area. Even though
think about area, like, the first thing we were talking about where I said percentile, 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 you have to think, when you think area, you have to think percentile because you're counting up. So 0.85, don't use 0.15 because it's going to get you that lower amount. Okay.
It's going to give you the answer to C.
Right.
Right. And so she wants to be in the 85th percentile. In the top 15% means you're in the 85th percentile. And then we're using the same mean and standard deviation. And when I mash OK, it's going to give me the magic number. Oh, actually, he's not going to quite make it. He's staying, technically, he hadn't made it. He's not going back to 1985. And if you don't know what we're talking about, it's okay. But it's about 88 miles an hour. But it's a little less than 88. So if you're a movie buff, he didn't quite make it.
I just hate that.
Yep, he's stuck in 1955. If you have never seen the movie, you have no idea what we're talking about and why we're geeking out.
So if I'm doing inverse normal, I'm having a hard time. This takes me forever.
You have an iPad.
I know, but I like the screen on my computer better. Okay. So I'm doing inverse normal, and we're using that 0.85 as the area. The reader really likes you to draw a picture, so I always recommend you do that. And my mean, and my standard deviation, right? And that's going to give me 88 miles per hour.
You're such a dork.
Like I said, enjoy your Christmas break and watch some Marty McFly. Okay, guys, I hope this video kind of reminded you how the normal distribution works, how to work with percentiles, how to work with probability that something's going to occur, and then also how to use that inverse normal feature on your calculator, okay? This particular, will you clear screen? Assignment is a Google Doc, so you're gonna go find 5.2 assignment. You're not on Khan Academy again yet. And I hope that you are having a good time, having a great time. Okay, bye.
Bye.